All right, so this is going to be part 3 of homework 4, which is all about uh, doing the taxi service problem. We're going to go over 3 things in this video. First, reading in the file, which is confusing at first, which is why I figured I'd go over it. Uh, and then fiddling your bits, because people find that very hard. Bit fiddling is one of those very tricky things in computer science that a lot of people don't really understand. But it's actually not too bad once you actually take a look at it. And then searching. So how do you actually find the solution to this homework problem? All right, so first I'll start with reading in the file. It's not very complicated, but I thought it was confusing. So the way you do it, right, you have name, and then you have uh, what is essentially like your price, and those two are obvious. But then there's like a list of destinations, right? D1, D2, D3, right? And this goes to, D, I think 16, or no, D15. This the way it works is in your places.txt file, you're gonna have 16 places, Schletter through Clemson Exchange. And the idea essentially is that uh, each of these places, so like Schletter is going to be mapped to D1. And the next on our list is Cooper Library, and that gets mapped to D2. So like for example, if this is, John's taxi service charging $5 and destination 1 happened to be something along the lines of Fort Hill, right? So if D1 is Fort Hill, then Schletter would go to, that means that you'd pick up from Schletter and go to Fort Hill. And then like if D2 was, you know, Fike, then that would mean that Cooper Library, you pick up from there and you go to Fike. All right, so now that that's out of the way, moving on to actual proper bit fiddling here. So it's gonna take a minute to understand like how this works, but essentially you only need 3 operations for this homework, right? You need the and symbol, which I can't draw an ampersand, so I will be doing a crappy one. The or symbol, which is like that, and the shift symbol, which is like that. The way that I would recommend going about doing this, right, is saying, basically checking because if you're using an integer, right, you're gonna have 16 ones. Right, so you have 16 ones, and all of these guys are going to map somewhere based on your values, right? And so the question is going to be, how do you move everyone around using just their bits? The idea being that, let's say you had like a 0 here and a 0 here, and we're only going to do up to there. So I'm going to put like maybe a 1, 0. All right, so if we have this guy and this guy going here with this guy going here, and this guy goes here, this guy goes here, this guy goes there, this guy goes there, and this guy goes here. The idea is that a 0 will not actually transfer into our answer. So even if the answer from a full set, so if our answer from this set would end up looking like 1, 1, 0, 1, 0, 1, 1, 1, because this one goes here and this one also goes there. Uh, then this guy goes here and this guy goes straight down. This guy goes here. Um, and then the 0 bit was going right there, but he didn't. So it would look like that. And my point, I guess, is that you need to figure out how to carry your zeros to keep them staying zeros, while at the same time bringing a 1 down to where it's actually supposed to go. So how would you do this? First, you need to check if in our top row here, in our first input number, um, so that's step 1. How do you figure out if the input at a bit is a 1? So the way you would do that is you would basically just say, all right, so at bit, right, this is just going to be an integer value. For example, if you had 4 bits that are all ones, then at bit 3, would be actually this is I think you start at 0. So at bit 2, which is this one, you see that it is a 1. Um, so this is just really an int. And then the other thing is you want to just check if it's a 1, right? So the way you would do this is essentially saying that, let me scroll up so I don't misspeak here. If, also, we're going to call this your state. So basically say if state and um, 1 shifted over to your bit. Or I guess a better thing would be to say shifted to your place. So essentially what this is saying that if your place, right? It's like if you start and you label number 1 as Cooper, then or you label bit 0 as Cooper, then you would say if state and 1 shifted over 0 times, which would look like if this is state, then 1 shifted over 0 times is this. So if these two guys, then we do a statement. Um, and that's what this is saying, right? So if our place, if we move over, right, then we made our place, I forget what was, I don't know, we can make it random. So if this guy was Fike, right, then we would say 1 shifted over 0, 1, 2, 1 spot, or 0 spot to 1 spot to 2 spot. So we make this guy right here a 1. And we say if state and this guy. And then that gives us our answer. Um, however, comma, um, this this also kind of works for untrueness as well. So if we're not at Fike, then that means that we've shifted our bit over 1 or to 0 to 1 to 2, then that means that this statement won't get triggered because this is not and, it is or. Um, and so we will not do our if statement. So what goes in the if statement? Next question, right? Uh, the if statement is going to be actually moving a bit into place, right? So if we're if we're picking up from point 0, so I guess point 0 I said was what, Cooper? So if we're picking up from Cooper and we want to bring ourselves to Fike, which is point 3. So from 0 to point 2. If we want to go from 0 to 2, the way we'd do that is we check if we're at Cooper, right? Or we check if we're at Cooper, in which we are in this case. So then what we would do is let me erase this kind of, I feel like it might confuse people if I leave it. Um, so this is where the taxi is going, right? So what you would do is you'd start with a temp variable. You'd start with basically a temp, which is just all zeros, and he is going to be your new state. And the way you would do this is declare temp equals 0, and that instantly just sets all of your bits to 0. So we would say, all right, if we're here, then we go here, and we mark temp right there as having this bit. So that would basically be saying temp is now equal to temp, right? So because we want to, if we have other bits that have been flipped, if this guy has theoretically a 1, we want to save him. We can't just get rid of him. So temp is equal to temp, but we're going to add something to him. We need to make temp more than what he currently is, a better variable. So the way you do this is we say temp or, that way, uh, like if there's already a 1 here, then the or will get triggered and it will become a 1. Also, we're going to leave this 0 for now. So what we're going to do is we're going to say it's temp or 1 shifted to, I guess, new place. And that's it. From there, we're going to say, all right, so temp is now equal to temp, and then temp shifted to a new place since we're going from, like I said earlier, 0 to 2. Our new place would be 2, our old place would be 0. So we check. And so this guy gets flipped to a 1, and now we have successfully moved one person to one place. Uh, and so if we repeat this a bunch of times, right, this guy, going over here and this guy staying down, then what would happen is our result ends up looking like this, right? So this one got moved, so there's now a 1 here. And this one went down, so there's now a 1 here. But if we look, or this guy is never gone to, which means that if we made this guy, if our state, right, if we made our state have a 1 right here, um, and he went, I guess, to this one as well. Why not? What happens is we've gone everywhere except for here, which means that we've effectively reduced our solution size, or the number of states that we have, down to like this new state, which is smaller. And the idea is to eventually get it so that the whole number is 0001, where 1 is the one representing like the Clemson exchange. And that's done basically just with this if statement. It's actually like really simple looking. But it took me a scarily long time to come up with. Um, and so what do we actually do with this information, right? Because this all here moves us from one one location to one destination. That doesn't really like help us a lot in the grand scheme of things. So what we would have to do is you'd want to do a for loop, right? So you'd have a for loop also, just for, I'm going to call this like the bit shift to reduce the amount of writing that I have to do in a second. So essentially what we do is we say for all of the integers in our, um, I guess, trip set, which is to say for every uh, move a taxi does, which um, is, I guess, a good way, or a better or a different way of saying, like, for every set of integers where you have a start and a destination, right? So, you pick up from Schletter, you pick up from Cooper, you pick up from all these places. For every move where you have like this, I'm just gonna make these all zeros for now because I haven't actually moved anywhere. So essentially, for every one line right here, that's a move, that's a move, that's a move, that's a move. So for each line, we just do this bit shift thing. So we would start at 0 and we say, all right, we move this guy to here, for example. So this guy becomes a 1. And then, you do it for every move. And then this guy, where is he going? He's going over here. And so now this guy becomes a 1. And then, this guy will become a 1 when this guy moves over here, and this guy, and this guy, and this. And to make my life easier, I'm just going to have everyone else go to all of the rest of these. So what you could do is essentially just consolidate solutions. Because now you've essentially made your solution much smaller in that you now only have to deal with these 3. And so the idea is to figure out, and if you had another service, for example, that brought these 3 specific places to the exchange, where I'm just going to make the exchange like a 1 off to the side since no one picks up there. Uh, if you have a service that brought just these 3 places to the exchange, and you had everybody else be a 0, and I do realize that I have significantly reduced the number of like variables we have. And then all the zeros, it doesn't matter where these guys go. Um, and that's what you're doing. You're looking for a solution that consolidates your actual answers to one place, which is this place. Okay, so I've just said a lot of words, and I don't know how much of it made sense. I hope a lot of it made sense because that's the best I got for this one. It's really a confusing lab or homework, but the idea is very simple. It's just a shift of state to go from from state A to state B, and you know, the idea is to simply get it so that in the least amount of moves possible, we go from the state of all ones to a state of all zeros with a one at the end. Um, all right, so now, last thing, searching. How do we search? So first, we're going to want to make a graph of this. And in this case, your neighbors is actually a little bit interesting, I guess. So first, we need to imagine what is our start. So our start is actually 2 to the 16th minus 1, which, because this is a 1 followed by 16 zeros, so if you just subtract 1, it becomes a 0 followed by 15 ones. Um, wait, I think I said that wrong. Uh, okay. It's whatever 5 okay. It's 65,535 or it's 536 minus 1. This gives you a number that is 16 ones, all in a line. Um, and our objective is to get to the state. Let me just clarify. All right, that's 16 ones. And then our goal is to get to the state of 1, where there's 1, 2. God damn it. 1 away. That's our goal. So to go from this state to this state in as few moves as possible. Uh, and so the way we're going to do our search is, or I shouldn't even start the search yet. We got to build a graph first. So how would you get every possible state? Well, the most obvious way that you do it, and there's a way to make it go faster, but I'm not going to go into that here because I don't know how well I can explain it in a video. DM me on Discord if you have questions about how to make it go faster than this once you actually get the solution. Because transferring it from the very long solution that I'm about to give to the very fast solution takes like 2 seconds. Uh, okay, so how do you build a graph? So step one is to analyze and say, all right, what are our nodes? A node is a state that is, or it is basically literally any integer between, including and between these two numbers of 1 and 65,535, because that's literally every combination of bits between here and there. Um, and so what you do is essentially just call visit on each taxi service for each number. So 1, and then you visit taxi service 0 through 59, uh, and then you go to 2, which actually in binary looks like this, and then you call visit on 0 to 59, and 1 1, and so on, right? You just keep going, and that's it. So for about 65,000 numbers, you just visit all 60 taxi services. And that will build us our graph, right? Because our graph, all we want is to know. I should redo all of that and leave it up so people can. So what we do then is we have our, I guess, graph built, and then you just do a breadth first search. Much the same as the other two, where you're gonna want to save your best solution, where uh, if you've once you've if you finished part two, you know that instead of saving up your solution as the shortest distance, you save it as a lowest weight in terms of color. Well, this is going to be a lowest cost. Um, and so essentially you just say if we haven't been to so you call visit on every node, and if you haven't been to that node, then or you call visit on all of the neighbors, or I guess you know what the neighbors are now. So you would visit all your neighbors, and you would say if the cost of my neighbor is infinity, which you would have definitely set up before this, uh, then you would just add him to the queue and visit his neighbors, and that's kind of it. That's the whole thing. Um, so I'm not actually going to go in depth over what that breadth first search looks like because it looks almost the exact fucking same as what you've done the last two times in a row now. It's super similar. A node looks a little bit different, I will say. Um, I don't know how well this is gonna come out in terms of audio and drawing explanations, but a node in this case would be an int, yes. But also the thing is that I find that my life got much easier if I saved the taxi service that I took to get here. So like, for example, if my integer went from, 101 to 010, then I would say that this guy was a pair that is, and I took taxi service, 2. Then what I would say is he's a pair of 101 and 2. And this would be a node for me. A pair of two integers for me is a node, so that I am able to essentially store the node itself in the service taken. Um, and so that is, I found that to be very helpful when it came to printing my solution because I could just say incumbent is this and then print the solution, and I could basically just print out all of my taxi services. Um, But otherwise, that's kind of it. It's just like breadth first search, print the solution. Um, like it's super straightforward. Once you get past this absolute tornado of a concept, because this is so fucking confusing. But once you get past that, it's actually not bad. So yeah, that is it for homework number 4. Hopefully this has saved you a little bit of time and grief when working. Um, so yeah, that's it.